Material sciences are one of the major areas of laboratory research that the International Space Station supports, and a new instrument from the European Space Agency is just being put into operation in that area. The Electromagnetic Levitator was delivered to the station last year on the last automated transfer vehicle and set up in the Columbus Laboratory module, and is being prepared for its first operations. I spoke with Dr. Douglas Matson, an associate professor of mechanical engineering at Tufts University, who serves as the EML's U.S. facility scientist, and as a speaker of the International Working Group representing all scientists doing research with EML. I asked him to start by describing this new facility and tell me what it's capable of doing.
The electromagnetic levitator involves passing a high-frequency current through copper-cooled coils. This current generates a magnetic field which causes the sample to levitate without touching anything. Therefore, we can process samples of metallic substances in a very clean environment with accurate control within the processing chamber. So what we look at is we look at how metals solidify, what the thermophysical properties are of those metals so that we can do process modeling here on Earth. And we look at the kinetics of the process. How do you change from one crystalline structure to another?
So tell me, why is it valuable for scientists to study the behavior of metals in the weightlessness?
The weightless environment allows us to do things that we can't do here on Earth. Specifically, since the sample is levitated, here on Earth, that means the sample itself is pulled down into the sample coils. Now, therefore, that creates a lot of stirring within the sample, which is not what we'd like to have. We'd like to have a quiescent sample so that we understand what is happening to the liquid itself. So therefore, in microgravity, since the sample's its weight doesn't have to be overcome, you can use a lot less magnetic force, and therefore a lot less stirring occurs. So you can look at a quiescent drop, take a look at its properties, and get much better thermophysical properties or much better understanding of how the droplet solidifies. The other thing we can do is we can look at how does stirring influence how solidification occurs. So this is something that's both the thermophysical properties and the influence of convection are extremely important for process modeling, for processes here on Earth. So it's not that we're solidifying a sample in zero gravity. It's more that we have better experimental control in order to provide better properties and the better ability for people to model earthbound processes and therefore create much better process control with higher quality products here on Earth.
What is the role of the astronauts on the station during the experiments using the electromagnetic levitator?
The astronauts' role is to act as our hands and our eyes. They do a lot of the equipment monitoring. They install the facility. When we take our samples from ground and bring them to our facility, it comes in a big giant box called a sample carousel. It's a carousel because the samples spin on inside this box. And so there's 18 samples that are going to be processed at any one time. We have multiple times that we're going to be bringing different carousels up. So the astronauts install our samples on our facility and then safely pack up the samples so that they can be brought back here to Earth so we can study how the samples solidified and what kind of structures we have formed during their solidification on orbit. The other thing that the astronauts do is they go in and they will change out equipment that we need for a specific experiment. For instance, we have two different camera systems. One that has very high spatial resolution so we can see fine details, and one that goes extremely fast so that we can look at processes that occur quickly. In order to change out these cameras, we need to have the astronauts go in. And as a matter of fact, during a past shuttle mission, during my experiment, the cameras stopped working and the astronauts had to go in, check the system out, they found that one of the cables was malfunctioning, and they were able to change that cable out and allow me to do my experiments. So the astronauts do a lot for us.
Can you give me some examples of some of the science experiment runs that you have planned for the astronauts on station?
All right, we have many different international collaborations on using our facility, where one of the projects is looking at thermophysical properties and how we could use those properties then in process modeling here on Earth. We have a project on sedimentation, looking at demixing and interfacial tension, one on development of composite structures, one on magnetic materials, and development of turbine blade materials. And finally, we have one looking at icosahedral order and quasi-crystal formation. So we have a multiple array of many different projects that are involved looking at how metals solidify differently depending on what their composition is.
How many researchers around the world are actually using this hardware that you have?
Currently, we have 14 European teams, 4 U.S. teams collaborating with them, 1 Canadian team, and I believe 3 Asian teams. So that involves about 50 scientists worldwide. We also have a rather large support structure and from ESA and from NASA and the Japanese Space Agency JAXA and the German Space Agency and Airbus. Those are the people who actually build the facility. So it's over 100 people who are involved with this project.
Thank you for your time today and explaining all of the science that's going on and all the work that you're doing. Thanks so much.
Thank you very much.